So, we're on Module 12, which means that we're going to be dealing with acidic and basic salts, finding the pH of the salts, solubility rules, the solubility constant known as KSP, finding pH from KSP, and finally Lewis acids and bases. So for this video, we're going to be focusing on acidic and basic salts, and if you guys remember from buffers, salts dissociate completely, meaning that what you end up with is what you started with following stoichiometry. So like if something was doubled, you're going to have to double that concentration and so on, but you're just using what you started off with. The only thing that we're going to do now is that we're going to determine if our salts are acidic, basic, or neutral. And essentially, for an acidic salt, you're going to have the conjugate of a strong acid plus the conjugate of a weak base. For a basic salt, you're going to have the conjugate of a strong base plus, plus the conjugate of a weak acid. And finally, for a neutral salt, you're going to have a conjugate of a strong acid plus the conjugate of a strong base. So essentially what that means is that, take for instance an acidic salt. So a weak base would be ammonia, right? And the conjugate of ammonia would be NH4 plus. And then the conjugate of a strong acid, let's say hydrochloric, would be Cl minus. So the acidic salt would be NH4 Cl, also known as ammonium chloride. And like I said, this is our conjugate of a weak base, and this is our conjugate of a strong base. And essentially what makes this acidic, like to think about it, is that if I were to do NH4 plus water, because we know that our salts dissociate completely into our NH4 plus and Cl minus in this case. So if we were to put that into the aqueous solution, we would end up with NH3 plus H3O plus, and this H3O plus that we're creating makes it acidic, right? Because we're increasing the amounts of H's in solution with an acidic salt. So our pH of an acetic salt would be less than 7. And then a basic salt, let's take the conjugate of a strong base, the Na plus from sodium hydroxide, and the conjugate of a weak base, which is going to be the acetate ion from acetic acid, which is a weak acid. So our salt would be sodium acetate. And so this is our strong base, weak acid. And what makes this acidic is if we were to throw this into solution and we have our acetic acid, well, acetate ions floating around in the water, we would create the acetic acid and the OH minus. And the OH minus is what tells us that it's going to be basic. So for a basic salt, our pH is going to be greater than 7. And then neutral salt, so Na from sodium hydroxide, Cl from hydrochloric acid. We have our salt, NaCl, strong base, strong acid. And if you guys remember what I said before about how our strong acids are strong because they dissociate completely, as in their ions do not connect to water or anything else afterwards, like they just remain like that, just surrounded by water. That's what happens here. So these neither raise nor lower your pH. So of a neutral salt, your pH is going to be equal to 7, if not very close to it, to keep it neutral. Right. So then we can do some examples of determining if a salt is basic, acidic, or neutral. So then let's take, for instance, the salt NaHCO3, which you guys may know as baking soda. So yeah. So then let's think about our things. So we have our Na plus and HCO3 minus. So these are conjugates, and our Na, we usually think about it as coming from NaOH, and HCO3, H2CO3, which is carbonic acid, which is a weak acid. So if we have a strong base, and a weak acid, would this salt be acidic, neutral, or basic? Cool. So hopefully you guys said that it was basic. I misspelled basic, oh my god. Basic, right? So if it's basic, our pH would be greater than 7. Cool. So then another example would be NH4 Br, or ammonium bromide. So your NH4 and Br, okay, this is a minus, and this is a plus. So our NH4 is the conjugate of NH3 plus water, and our Br is the conjugate of HBr. So, okay, our NH4 we know is the conjugate of our weak base, right? And then HBr, hopefully you guys remember, is a strong acid. Yeah, strong acid. I'm right. So if we have a weak base and a strong acid, would it be neutral, acidic, or basic? So hopefully you guys said acidic. And our pH would be less than 7. So yeah, that's pretty much just how you determine our salts. It's if you were to put them in solution, what would essentially your weak thing give you? Because your NH4 plus, like I said before, if you were to put that in water, it would give you hydronium ions, which is why it's acidic. Whereas with the HCO3, if you were to put that in water, it would accept your H pluses, so it would give you OHs, which is what would make it basic. Yeah. So then the next thing that we're doing is we're solving for pH of salts. Which, if you guys remember, we kind of did that with titrations when we had an equivalence point and the last thing we had was a salt. But yeah, so it's just knowing the conjugates, and like I said, they kind of help determine the pH of your solution when you're adding them into it. And you guys should just remember, if your salt's acidic, basic, or neutral, you should know the range of your pH. Because like I said before, if it's an acidic salt, your pH is going to be less than 7. If it's a basic salt, your pH is going to be greater than 7. And a neutral salt, your pH is going to be about 7, right? So that's just kind of to keep in mind for you to double check yourself when you're working with it, because if you have a basic salt and you end up with a pH that's less than 7, then you probably messed up somewhere along the way, and like double check yourself, you know? But okay, we're gonna do an example just because I think that's the easiest way to put these things into perspective, because there's not much to explain. But let's say we have 0.5 molar of ammonium bromide in water. And the Ka for ammonium is 5.56 times 10 to the negative 10. So we're determining the pH of this solution. So the first thing we're going to do is set up an ice table for our salt, which essentially, like I said, it breaks apart fully, so you end up with your ammonium ion and your bromide ion, and then you start off with 0.5, none of these, and then you're subtracting 0.5 and adding 0.5 to these, because like I said, what you started off with is what you end up with. So at the end you have 0, 0.5 molar, and 0.5 molar. And when we're determining the pH of a salt, we usually do it with the conjugate of the weak, because the strong isn't going to want to go back to being the acid. It just stays as an ion. So then this is essentially step 1. So then step 2, we were to take NH4 plus, add water to it, and now we do have double arrows because this is a weak base, well, conjugate of a weak base, so it is going to go back and forth. So we're going to end up with ammonia plus our hydronium ions. And then this is a liquid. These are aqueous and aqueous. So then initially we have the 0.5 molar that we took from over here, and then you don't deal with your condensed states, 0 of these, and then your change is going to be X because we don't know how much these dissociate by. So then at equilibrium we're going to have 0.5 minus X, X, and X, right? So then our step 3 would be to solve for our X using Ka, which we were told is 5.56 times 10 to the negative 10 is equal to your products, which I'm just going to put as X squared because X times X gives you X squared, times 0.5 minus X. And this number is small enough that we can just disregard the X. So then we would have 5.56 times 10 to the negative 10 times 0.5 is equal to X squared. It's just square root of this. So that X is equal to 1.67 times 10 to the negative 5, around about, like I said, rounding and so forth. So then our final step would be to find the pH, which is equal to the negative log of our concentration of hydronium ions, which we just solved for with X. So then we just input our X value into that, 1.67 times 10 to the negative 5, and we should get a pH of around 4.78. And that makes sense because, like I said, our salt ends up being, alright, I should have said that before this, but okay. So looking at this salt, we have the conjugate of a strong acid, the conjugate of a weak base, So it's in acidic salt. Oh, how did I do that? Okay, acidic salt. So our pH should be less than 7. And we ended up with a pH of 4.78, which is less than 7. So that checks out. Woohoo. So then we can do another example. And this time, let's do a basic salt. Or I just gave that away, but basic salt. I'm gonna need more room for this time out. Okay, there we go. So let's say that we have 15 grams of sodium acetate in 3 liters of water. So we're gonna find what is the pH, and then Ka for acetic acid is equal to 1.8 times 10 to the negative 5. So our first step here is going to be to figure out our moles of sodium acetate. So we're going to do 15 grams over its molecular weight, which for me ended up being 82 grams of sodium acetate over 1 mole. So we end up with about 0.061 moles. Oh wait, no, my bad. We end up with 0.18 moles, around about there. So then to find our molarity, we just divide it by the 3 liters of solution, and we end up with 0.061 molar. So then our second step is to set up our ice table for the salt, just so that you guys can see where I'm getting the numbers from. Where we initially have our 0.061, 0, and 0, minus 0.061, plus 0.061, so that this ends up in 0, and then both of these are 0.061 molar. So then our third step is to take our conjugate, which in this case is the acetate ion, put it into our water solution, double arrows, we end up with acetic acid and OH minus. This is a liquid. These are aqueous. So initially we have the 0.061 from our salt, and these are 0. And then since this is our weak, well, the conjugate of a weak acid, we have our change is x, because these don't dissociate fully, so we don't know by how much they're dissociating. So we end up at equilibrium with these values. And then we're going to solve for our x's, which we have an OH left over, which if we have an OH, that means we have to use Kb. And since we're given Ka, we're going to have to do Kw divided by Ka gives us Kb, which is 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So our Kb ends up being 5.56 times 10 to the negative 10. So now we can solve for our x's. Oh, whoops. Okay. 5.56 times 10 to the negative 10 is equal to x squared over 0.061 minus x. We can get rid of our x because this value is small enough to negate it, essentially, like it's negligible. So then we end up with 0.556 times 10 to the negative 10 is 0.061 is equal to x squared. So we end up with our x being 5.82 times 10 to the negative 6. So then, I guess over here. Step 5 would be to find our POH, because our X is our concentration of OH, which is negative log concentration of our OH ions, which is whatever our X is, 5.82 times 10 to the negative 6. So we should end up with a POH of about 5.52. Yes, I think that's what I have written down. Or a pH around that, POH. So then to find pH, we would do 14 minus 5.52. Let me do that math again because I feel like I wrote down the wrong number. So log of 5.82 to the power of negative 6. I did. Yeah, okay, this makes more sense. 5.24. So then you do 14 minus that number, and you should get your pH to be 8.76. Right. And then, as I said before, you double check by just, so our original salt was sodium acetate, and this is our conjugate of a strong base plus, conjugate of a strong base plus the conjugate of a weak acid equals a basic salt whose pH should be greater than 7, and our pH is greater than 7, so that checks out. And that's pretty much all you have to do for finding the pH of your acidic or basic salts. And then once you get a neutral one, all you guys have to do is tell me that it's about 7 or very close to 7, just because you have strong plus strong shouldn't change the acidity of my water. So yeah, that's pretty much it for this one.